So now we're going to talk about populations. There are terms these terms you've all seen. Sometimes use them incorrectly. Incorrectly in the form of you're not using them in the way that science uses them. So population is a group of the same species living in a given area. So it must be the same species in a given area. Community is all of the different populations, so different species, living and interacting in that same area. And that's why it's underlined and bolded, because community is really dealing with all the populations in a given area. And now the ecosystem is the community with the abiotic factors. So all the living organisms that are living in a given area, so several different populations, plus the abiotic, the non-living. So the example I'm going to use, what do we call us? We call us the Stevenson. Okay, when you're talking about, you live in the Stevenson
School district.
Okay, this is the first, thank you, community. This is the first class that's never said Stevenson community right off the bat. You're part of the Stevenson community, right? Are we saying, what? Are we actually the Stevenson community? We're going back. No, we're not. When we talk about, when you say Stevenson community, are you talking about the blades of grass? No, who are you talking about?
Students.
People. Students and teachers, all Homo sapiens, right? All the same species. So we should really be calling it the Stevenson population, because it's all the same species. Now, if I talk about the blades of grass, the trees, the bushes, the birds, the insects, the cockroaches, and the rats that live here?
The rats.
Yeah, oh, there's lots of rats. Then we call it the Stevenson community. If I add the water and the soil and the rocks, then it's the Stevenson ecosystem. Okay, no ecosystem. So we don't use the terms fully correct outside of science. Science, remember, is talking about population is just one species. Community must be multiple populations. So there has to be at least two different species in it. Okay? Habitat is a type of environment in which they live. So within an ecosystem, you have a habitat. That tree, there are organisms that are living in that tree. Insects. So yes, it's part of the ecosystem here, but the habitat is actually the tree. The niche, that's the role that organism plays within the habitat. So if you were to say a habitat of Stevenson ecosystem would be the athletic department. Anybody athlete in here?
Brian
Yeah,
Brown.
some. And so within that athletic department habitat, you have some that are in some sports, like track and field, cross country, football, basketball. Even within that specific sport, you have roles. You're a starter. You're a bench player. You're a lacrosse player. Okay, better? Okay, and we're going to talk about this. Shh. I have a different slide in a second to talk about what this actually means in a real habitat, not just the Stevenson make-believe niche. Come on. Okay, populations. Populations grow. We know this because we want to reproduce. That's the whole point of all of us being on this planet, is to survive and reproduce. But most populations are impacted by what's called limiting factors. These variables that will stop the growth of a population. Yes?
Why is it most and not all?
We are an exception to the rule. Humans are exception to the rule, and I'll get into that.
Humans are accepting what?
Humans are the exception to the rule of limiting factors right now. Growth will depend on the rate of reproduction. If you reproduce, you grow more. If you don't reproduce, you don't grow more. Humans are ever increasing. Anybody know what number that we've reached for our population? 7 billion last year is what we've reached. there's questions, and some governments actually put this in place, that there is an allowance of how many children you can have. China, right? China, and I guess I thought it was no longer there, but apparently it's still a law that you can only have one child. If you have a second child, several things could happen. One, you get fined, and then there's also a lot that give up for adoption. Twins, someone asked that third hour. I have no idea, but someone said that you have to pay. So, okay. Okay. So the question is, will there be a point where we might reach that level that we no longer can successfully live? Meaning that we can't have all of the products that we need, all the resources that we need. And so that's governments. And we're not at that point yet. I'll show you a slide where, and we'll talk about what point we might be getting there. But that's going to be something governments have to, think about. That show, 19 and counting, or is she on 20 already? I don't know. But that's 19? I don't know. Maybe, but still has 19 kids. So you have to think about that. Oh, that's John and Kate Placate. They got divorced. If nothing limits that growth, if there are no limiting factors, the growth curve is said to be a J-shaped curve or an exponential growth curve. And so each generation thereafter will increase, continually and continually increase. No matter what the rate of growth, it will always be that J-shape. It continues to increase. This is humans. Right now, we do not have a limit to our growth. We can successfully survive and reproduce right now without anything limiting our growth.
Do we not have limit, or is it not?
At this point, we haven't reached it. We don't know what our limit is.
But there is.
We don't know. What can impact the growth? 4 factors. 1, birth rate. Natality means birth rate. Anybody in human geo? No? If you take human geo, I believe you talk about this. And now think of it not in human. Think about other organisms. Their birth rate. Immigration, meaning organisms moving in, a set of species moving into that area. Death rate, the death rate, mortality rate. And then emigration is those species moving out of the area. And what really happens is when you have major climatic changes, the tsunami in Indonesia, I think that was that one. They actually said that a lot of the animals were able to sense that was happening, and so they emigrated out. And so that changed the entire habitat because those animals emigrated out. So that's what causes the growth rate to fluctuate. Age structures can indicate future growth. That's really, we're not going to talk too much about it, but it's really happening for us. We have these scientists that try to predict the number of people at each age group, which will mean how much Social Security we're going to need, how much Medicare, Medicaid, health insurance, all of that stuff. And we need to predict that outcome so that we have money and resources for the future and medical supplies for the future. So when you talk about populations that have limiting factors, which is almost every other organism, there's going to be a rate at which they can survive. So when you have some factors that are short in supply, hey, food. What's going to happen? You're going to compete for that food. Is everyone going to survive? No. So food would be an example of a limiting factor. It will prevent that exponential growth from taking place. In this growth curve, you have what's called a carrying capacity. It's the amount of organisms or individuals within that population that can survive, that area can support and survive. That is known as an S-shaped growth curve. Because you won't continue to grow, you'll reach your carrying capacity, and one of two things happen. You'll go above your carrying capacity. Do you think you can survive above your carrying capacity? No. So what's going to happen to some organisms? They're going to die. So then you'll take a dip down below the carrying capacity, and then eventually go up above. So you're going to really hover around that carrying capacity. You don't need to know this equation. Just showing you the graph. So the carrying capacity, it's a constant. In this class, we have right now 23 individuals. So the carrying capacity actually is 25, right? We have 2 desks, or 2 chairs that are not being used, and I'm in the teacher chair. So we have 25 as our carrying capacity. We have not reached our carrying capacity. And so the counselor might transfer another person in here. We have Shep, so he will be here, but we might transfer another person in here. Then we will have reached carrying capacity. What if the counselor transferred 3 more individuals in here?
It wouldn't work.
It wouldn't work so well. One or a couple people might not perform as well. There's not seats really for them. They might not be able to see. So let's change it up into talking about actual resources. Okay? We have 25 desks. So that's, let's say, or 25 chairs. That's our carrying capacity. Now I have you. I'm locking you all in this room. Your parents signed off. They're okay with it. You get all of your food and water, but we only get 20 sets of meals each day. What's going to happen?
Brian's going to starve.
Brian might starve. Why?
Because he won't get any meat.
Because nobody's going to let him get the meal. So what's our new carrying capacity there? 20. 5 of you will compete, or all of you will compete, but 5 of you will not survive. And if you say, oh, but I will share with Holly, don't worry about it. Is that what regular organisms will really do? No. A lion is not going to go to another lion, hey, you're my buddy, I'm going to share. No. They don't do that. They fight for their food. Okay? So it depends. So food, resource, is a limiting factor. We have 2 types of limiting factors. We have density-dependent limiting factors, and we have density-independent. Density-dependent, it really matters how dense, and I know that's a bad word to use in an actual definition, but it matters how dense that population is. And I'm going to give you examples. Disease. If you were to, I wouldn't do this, but if you were to have someone have swine, do a biological warfare or whatever in an apartment building downtown, and do the same thing in a rural area, which one's going to impact more people? The apartment downtown, because it's more dense. So disease is a density-dependent factor. So it's competition, so the resources, competition for resources. Like I gave that example in here. And predation, if you have more prey or less prey in a given area, that depends on how many will survive and how many won't. The density independent does not matter how dense. Hurricane going to hit that apartment or hit the rural area? Do you think it's going to say, hey, there's more people over there. I prefer to wipe out that apartment. No, it's going to hit wherever it hits. Natural disasters are going to hit no matter what. Seasonal cycles, all that stuff. It does not matter how dense that population, it's going to happen. Human intervention, that means Las Vegas, I want to build another hotel. I'm not going to worry about the different insects that live on this, if it's more dense here versus there. I'm going to build where it's more profitable for me, and that could have wiped out a whole population. Malthus was a scientist. He talked about how populations, there is a limit to the population, and disease is going to be one of the reasons why the human population will eventually, he feels, will turn into that S-shaped curve. So that brings us to the question, is there a limit? You have just the top one on the right. That's the newest version. The one from, 15 years ago is the one on the bottom left. I put both of them up because you can actually see how it's kind of changed from a true J-shaped. So we're still J-shaped because we're at 2012, 2013. But it looks like what type of curve now? Going to turn into what type of curve? An S-shape. This website feels that when we reach 9 billion at 2048, that might be our limit. It's just a guess, an estimate. The reason why I put both up there, one, to see how the different curves look now, and to see in 1998 the predicted amount in that we would get to 8 billion in 2028. Now, what's the predicted date we'll get to 8 billion? 2024. 9 billion in the bottom left, so 2054, whereas the top, it says 2048. So we're predicting earlier and earlier, which that's why I think that it's changing to an S-shaped curve. And we're going to have to, the world, not just the U.S., but the world will have to figure out what to do about this. I don't know, and I'm glad I don't have to worry about that problem.
We gotta go to Mars. The only way out.
Mars, you're right. This is different than yours. The individuals, everything's the same except for I talked about something that's actually in your book, and you should have read this. So if you want to cross off the two scientific names and put these up instead. These are the barnacles. Do you remember reading about the barnacles? This is how you get your niche. So you have two different barnacles. The C. stellatus, which is the small barnacles, and the S. balanoides, which are the large barnacles. The red fundamental niche is talking about the smaller ones, the C. stellatus, and they could live in shallow or deep water. The S. balanoides, they could only live where? In the deep water. So when you take two different organisms, put them in the same area, they're going to compete. So the large ones compete and won, and so they were able to take over the deeper area, which is still their fundamental niche. Their fundamental and realized were the same, but now the shallow got pushed up, the C. stellatus got pushed up to the smaller, the top, the shallow, and that became their realized niche because of competition. So that's one type of interaction that plays, is competition. Predation is another one. I don't need to really go over predator-prey, right? You know predator-prey relationships? Yeah? And this is our very last slide. Yay! The last set of interactions, which you'll really see a lot of in the movie tomorrow, symbiotic relationships. It's where two species are interacting with each other. So one species lives in close association with another species. They have to be two different species. It's key. And we talk about really three different symbiotic relationships. Mutualism. If you think of mutual friends, you like each other. That's where both organisms will benefit. Pollinator and plant. Pollinator will get the food, and the plants will be able to get pollinated. You have E. coli in your large intestine. Do you remember why you have E. coli in your large intestine? What does it do for us? It makes...
Bacteria.
E. coli is bacteria. The bacteria makes vitamins in our large intestine. So it's good that we have the E. coli in our large intestine. They make vitamins. What does E. coli get out of it? They get food. They get to feed off of our feces. That's a beneficial relationship for both of them. Parasitism. Parasites. Do we like parasites? No, we get harmed. Parasite benefits, but we get harmed. Ticks, fleas, lice, they feed off of, mosquitoes feed off of our blood. They benefit, and we get harmed. Commensalism, that's where one benefits, and the other one is neither harmed nor helped. One that many, many, many of you have seen the movie, Finding Nemo. Who needs an enemy, or what is it? Who needs friends? I don't remember that joke. When you have anemones. The sea anemone and the clownfish. Clownfish gets helped, benefits, because it gets to, with friends like these, who needs anemones? There's the joke. The clownfish benefits because it can hide in the anemone. The anemone neither gets harmed nor benefits. And then what we're having a lot of problems occurring in the U.S. are the introduction of invasive species. Either intentionally, we go to an exotic location, find a plant, bring it back on purpose, or accidentally, and that was a big West Nile thing where we went and we bring produce or something, or the Asian longhorn beetle. I don't know if anybody's heard of that when we bring things back in the crates, you've got these insects in it that then come accidentally to our place. And that invasive species can take over the ecosystem and really change things. And that is all she wrote.